Vibration analysis, fast Fourier Transform or FFT, transforming signals to reveal hidden vibration patterns. What is vibration analysis? Vibration analysis is a critical technique used in predictive maintenance and condition monitoring of machinery. It involves measuring and interpreting vibration signals to detect imbalances, misalignments, bearing failures, and other mechanical issues before they lead to catastrophic breakdowns. Vibration occurs when a machine or component oscillates around its equilibrium position, and these oscillations can be recorded using sensors such as accelerometers. The raw data collected is typically in the time domain, showing how vibration amplitude changes over time. However, analyzing this data directly can be challenging because complex machinery often produces vibrations composed of multiple frequencies. By studying these vibrations, engineers can identify patterns that indicate specific faults, such as high-frequency signals pointing to bearing defects or low-frequency signals suggesting imbalance. Vibration analysis is widely applied in industries like manufacturing, aerospace, automotive, and energy, where reliability and uptime are crucial. Understanding vibration behavior allows maintenance teams to schedule repairs proactively, reducing downtime and operational costs. This technique not only improves machine health but also enhances safety and efficiency across industrial operations. Fundamentals of fast Fourier Transform. The fast Fourier Transform, FFT, is a mathematical algorithm that efficiently computes the discrete Fourier transform, DFT, of a signal. It transforms data from the time domain into the frequency domain, enabling engineers to analyze the frequency components of complex signals. In vibration analysis, FFT is essential because machines generate vibrations that are combinations of multiple frequencies. By applying FFT, these frequencies can be separated and visualized, making it easier to identify which components correspond to specific machine parts or faults. For example, an imbalance in a rotating shaft typically appears as a peak at the rotational frequency, while bearing defects often show up at higher harmonics. FFT works by breaking down a signal into sinusoidal components, each with a specific amplitude and phase. This decomposition provides a clear picture of how energy is distributed across different frequencies. The algorithm is highly efficient compared to traditional Fourier transform methods, reducing computational complexity from O(n) squared to O(n) log n, which is crucial for real-time monitoring applications. Understanding FFT is fundamental for engineers who need to interpret vibration spectra and diagnose machinery health accurately. Why use FFT? Importance and benefits of FFT in vibration analysis. FFT offers several advantages in vibration analysis, making it the preferred method for frequency domain studies. First, it provides a clear representation of the frequency components present in a vibration signal, which is critical for diagnosing machine faults. Many mechanical issues manifest as distinct frequency patterns, such as imbalance at the fundamental frequency or gear defects at specific harmonics. Second, FFT enables early detection of problems by revealing subtle changes in frequency spectra that might not be visible in time domain data. This proactive approach helps prevent costly downtime and extends equipment life. Third, FFT supports trend analysis by allowing engineers to monitor changes in frequency peaks over time, which can indicate progressive wear or deterioration. Additionally, FFT is computationally efficient, making it suitable for real-time monitoring systems that require quick processing of large datasets. By converting complex vibration signals into an easily interpretable format, FFT enhances decision-making and maintenance planning. Its ability to pinpoint the source of vibration issues reduces guesswork and ensures targeted repairs, ultimately improving reliability and operational efficiency. Understanding domains, time domain versus frequency domain. In vibration analysis, signals can be represented in two primary domains, time and frequency. The time domain shows how vibration amplitude varies over time, which is useful for observing transient events or overall vibration levels. However, time domain data often lacks clarity when multiple frequencies are present, making it difficult to identify specific fault signatures. The frequency domain, obtained through FFT, displays amplitude as a function of frequency, providing a much clearer picture of the underlying components. For example, a time domain signal may appear as a complex waveform, but its frequency domain representation could reveal distinct peaks corresponding to rotational speed, bearing frequencies, and gear mesh frequencies. This transformation simplifies fault diagnosis by isolating individual frequency components. Engineers often use both domains together, the time domain for detecting sudden changes or impacts and the frequency domain for detailed analysis of periodic phenomena. Understanding the relationship between these domains is essential for accurate interpretation of vibration data and effective maintenance strategies.